Current source IB is removed from consideration by replacing with an open or infinite impedance path. A Kirchhoff's current law analysis of the as-analyzed circuit indicates there is only a series path through impedance element Z1 and Z2. Because of the inclusion of the open, there will be no current through impedance element Z3. Given the assumed direction of current travel, polarity of the individual voltage drops will be as indicated. Since impedance element Z3 experiences no current, it will experience no voltage drop. A Kirchhoff's voltage law analysis of the loop in orange indicates EA equals V1 plus V2. This purely series circuit is a perfect setup for the voltage divider rule. An application of the voltage divider rule demonstrates that V1 is 21.3 volts at an angle of 27.6 degrees, where polarity is assumed positive to negative, bottom to top. Application of Kirchhoff's voltage law demonstrates V2 to be 11.1 volts at an angle of negative 62.4 degrees, oriented positive to negative, top to bottom. Let's now examine current. An application of Ohm's law demonstrates that I1 is 195.1 milliamperes at an angle of 27.6 degrees, traveling bottom to top. Given the removal of current source IB has created a purely series circuit, it can be said I2 equals I1. This completes the analysis from the perspective of voltage source EA. Let's do the same thing for sinusoidal AC current source IB. Stage 2 of this second illustrated example problem now dictates we solve for voltage across and current through each impedance element when current source IB is the source of interest and voltage source EA has been removed from consideration. Again, in addition to magnitude and phase shift, clearly indicate direction and polarity. Once we've got these values, we'll move on to stage 3 and summate our results, accounting for not only magnitude and phase shift, but also polarity and direction. By all means, pause the lecture and try stage 2 on your own. If you're tracking, you should have obtained the following results. Voltage source EA is removed from consideration by substituting a 0 ohm impedance path. A Kirchhoff's current law analysis of the as-analyzed circuit illustrates that current IB equals I3, and then current splits into two paths, a portion of which goes through impedance element Z1, and the remaining portion of which is routed through impedance element Z2. It can be said IB equals I3, which equals the summation of I1 plus I2. Given the assumed direction of current travel, voltage polarity would be as indicated. A Kirchhoff's voltage law analysis of this first loop in red indicates the voltage across current source IB equals V3 plus V2. A Kirchhoff's voltage law analysis of this second loop in orange indicates the voltage across current source IB equals V3 plus V1. Finally, a Kirchhoff's voltage law analysis of this third loop in yellow indicates V1 equals V2. These analyses imply that impedance element Z1 and Z2 are in parallel with one another. Application of Kirchhoff's current law demonstrates that I3 is 50 milliamperes at an angle of 0 degrees, traveling right to left. We now have a perfect setup for the current divider rule. We have a parallel combination of two known impedances, and we know our incoming current. Application of the AC current divider rule demonstrates I2 to be 44.3 milliamperes at an angle of 27.6 degrees, traveling top to bottom. Application of Kirchhoff's current law demonstrates I1 to be the remaining 23.2 milliamperes at an angle of negative 62.4 degrees, also traveling top to bottom. Let's now examine voltage distribution within this circuit. Application of Ohm's law demonstrates V3 to be 4.3 volts at an angle of 90 degrees, where assumed polarity positive to negative is right to left. Another application of Ohm's law demonstrates V2 to be 4.8 volts at an angle of 27.6 degrees, oriented positive to negative, top to bottom. Finally, given impedance element Z1 is in parallel with impedance element Z2, it can be said V1 equals V2. Voltage across elements in parallel is the same. This completes the analysis from the perspective of current source IB. Let's now summate our values. Stage 3 of this second illustrated example problem now dictates we summate the values of our previous analyses, accounting for not only magnitude and phase shift, but also polarity and direction. By all means, pause the lecture and try stage 3 on your own. If you're tracking, you should have obtained the following results. Note impedance element Z2 experiences voltage of the same polarity and current in the same direction for both sources. When these two aiding effects are superimposed upon one another, these effects would be additive. In contrast, note impedance element Z1 experiences voltage of opposite polarity and current in the opposite direction for the two different sources. When these two opposing effects are superimposed upon one another, these effects would be subtractive. Since voltage source EA's contribution has a larger magnitude, let's consider its assumed polarity and direction as dominant. Using this interpretation, current source IB's contribution would be subtracted from voltage source EA's contribution. Operating under this assumption, you should have obtained the following values. The opposing contribution of source EA and IB yield V1 to be 16.4 volts at an angle of 27.6 degrees, oriented positive to negative, bottom to top. I1 equals 150.8 milliamperes at an angle of 27.6 degrees, traveling bottom to top. The aiding contribution of source EA and IB yield V2 to be 12.1 volts at an angle of negative 38.9 degrees, oriented positive to negative, top to bottom. I2 is 212.7 milliamperes at an angle of 51.1 degrees, traveling top to bottom. Finally, given only source IB has any influence on impedance element Z3, V3 is found to be 4.3 volts at an angle of 90 degrees, where assumed polarity is positive to negative, right to left. I3 is 50 milliamperes at an angle of 0 degrees, traveling right to left. Alright, I believe we've accomplished our desired goals and can move on to our final illustrated example problem. Our third and final illustrated example problem features a series parallel combination of two sources and three impedance elements. Current source IA has a value of 150 milliamperes at an angle of 0 degrees. Voltage source EB has a value of 60 volts at an angle of 0 degrees. Impedance element Z1 has a value of 120 ohms at an angle of negative 90 degrees. Impedance element Z2 has a value of 150 ohms at an angle of 90 degrees. And finally, impedance element Z3 has a value of 133 ohms at an angle of 0 degrees. Stage 1 of this illustrated example problem necessitates we solve for voltage across and current through each impedance element when current source IA is the source of interest and voltage source EB has been removed from consideration. In addition to magnitude and phase shift, clearly indicate the assumed direction of polarity. Once we've got these values, we'll move on to stage 2 and examine voltage and current figures when voltage source EB is the source of interest and current source IA has been removed from consideration. By all means, pause the lecture and try stage 1 on your own. If you're tracking, you should have obtained the following results. Source EB is removed from consideration by substituting in a 0 ohm short circuit impedance. The inclusion of the short circuit has fundamentally altered the nature of our original circuit. A Kirchhoff's current law analysis illustrates source current splits into three paths. IA equals I1 plus I2 plus I3. The removal of voltage source EB has effectively placed impedance elements Z1, Z2, and Z3 perfectly in parallel with one another. Given the assumed direction of current travel, voltage polarity would be as indicated. A Kirchhoff's voltage law analysis of this perfectly parallel circuit indicates the voltage across current source IA equals V1 equals V2, which equals V3. Voltage across elements in parallel is the same. The parallel combination of impedance elements Z1, Z2, and Z3 presents a combined impedance of 129.8 ohms at an angle of negative 12.5 degrees. Application of Ohm's law demonstrates voltage across the combined impedance Z single prime to be 19.5 volts at an angle of negative 12.5 degrees. Given Z single prime is the parallel combination of Z1, Z2, and Z3, it can be said V single prime equals V1 equals V2, which equals V3. Let's now examine current. Application of Ohm's law demonstrates current through impedance element Z1 to be 162.3 milliamperes at an angle of 77.5 degrees, traveling top to bottom. Another application of Ohm's law demonstrates current through impedance element Z2 to be 129.8 milliamperes at an angle of negative 102.5 degrees, traveling top to bottom. Finally, application of Kirchhoff's current law demonstrates I3 to be the remaining 146.4 milliamperes at an angle of negative 12.5 degrees, traveling left to right. This completes the analysis from the perspective of sinusoidal AC current source IA. Let's do the same thing for voltage source EB. Stage 2 of this illustrated example problem now dictates we solve for voltage across and current through each impedance element when voltage source EB is the source of interest and current source IA has been removed from consideration. Again, in addition to magnitude and phase shift, clearly indicate direction and polarity. Once we've got these values, we'll move on to stage 3 and summate our results, accounting for not only magnitude and phase shift, but also polarity and direction. By all means, pause the lecture and try stage 2 on your own. If you're tracking, you should have obtained the following results. Current source IA is removed from consideration by replacing it with an open or infinite impedance path. Again, the inclusion of this open has fundamentally altered the nature of the original circuit. A Kirchhoff's current law analysis illustrates that source current must travel through impedance element Z3. It then splits into two paths. One path leading through impedance element Z1 and the other path leading through impedance element Z2. It can be said source current equals I3, which equals I1 plus I2. Given the assumed direction of current travel, voltage polarity is as indicated. A Kirchhoff's voltage law analysis of this first loop in red indicates EB equals V3 plus V2. A Kirchhoff's voltage law analysis of the second loop in orange indicates EB equals V3 plus V1. Finally, a Kirchhoff's voltage law analysis of this third loop in yellow illustrates V1 equals V2. These analyses imply that impedance elements Z1 and Z2 are in parallel with one another, a simplification I'm calling Z double prime, where Z double prime has a value of 600 ohms at an angle of negative 90 degrees. Impedance element Z3 and combined impedance Z double prime are in series with one another. This is a perfect setup for the voltage divider rule. An application of the voltage divider rule demonstrates V3 to be 13 volts at an angle of 77.5 degrees, oriented positive to negative, right to left. Application of Kirchhoff's voltage law demonstrates V double prime to be the remaining 58.6 volts at an angle of negative 12.5 degrees, oriented positive to negative, top to bottom. Given impedance element Z double prime is the parallel combination of impedance elements Z1 and Z2, it can be said V double prime equals V1, which equals V2. Voltage across elements in parallel is the same. Let's now examine current. Application of Ohm's law demonstrates current through impedance element Z1 to be 488.2 milliamperes at an angle of 77.5 degrees, traveling top to bottom. Another application of Ohm's law demonstrates current through impedance element Z2 to be 390.5 milliamperes at an angle of negative 102.5 degrees, also traveling top to bottom. Finally, application of Kirchhoff's current law demonstrates that I3 is the summation of I1 plus I2. This yields a value of 97.6 milliamperes at an angle of 77.5 degrees, traveling right to left. This completes the analysis from the perspective of voltage source EB. Let's now summate our previously obtained values. Stage 3 of this illustrated example problem now dictates we summate the values of our previous analyses, accounting for not only magnitude and phase shift, but also polarity and direction. By all means, pause the lecture and try stage 3 on your own. If you're tracking, you should have obtained the following results. Again, summating the contributions of the individual sources is relatively straightforward if one has a modicum of organizational skill. One must account for not only magnitude and phase shift, but also assume polarity and direction. Node impedance elements Z1 and Z2 experience voltage of the same polarity and current in the same direction for both sources. When these two aiding effects are superimposed upon one another, these effects would be additive. In contrast, node impedance element Z3 experiences voltage of opposite polarity and current in the opposite direction for the two different sources. When these two opposing effects are superimposed upon one another, these effects would be subtractive. Since current source IA's contribution has the larger magnitude, let's consider its assumed polarity and direction as dominant. Using this interpretation, voltage source EB's contribution would be subtracted from current source IA's contribution. Operating under this assumption, you should have obtained the following values. The aiding contribution of source IA in EB results in V1 being 78.1 volts at an angle of negative 12.5 degrees, oriented positive to negative, top to bottom. I1 will be 650.5 milliamperes at an angle of 77.5 degrees, traveling top to bottom. The aiding contribution of the two sources yield V2 to also be 78.1 volts at an angle of negative 12.5 degrees, oriented positive to negative, top to bottom. I2 is 520.4 milliamperes at an angle of negative 102.5 degrees, where the assumed direction of travel is top to bottom. Finally, the opposing contribution of the two sources yield V3 to be 23.4 volts at an angle of negative 46.2 degrees, where assumed polarity is positive to negative, left to right. I3 is 176 milliamperes at an angle of negative 46.2 degrees, traveling left to right. Alright, that's about enough illustrated examples for now. In conclusion, this lecture examines several illustrated examples of the superposition theorem as applied to multi-source AC circuits. We learned that linear properties like voltage and current can be summated, accounting for not only magnitude and phase shift, but also assumed polarity and direction. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.